Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Okay, grade 11s, the last topic I mentioned that we want to do is redox reactions. Okay, so for the purpose of this tutorial recording in class, we are going to be doing the topic redox. Alright, or redox reactions. This topic we did start in grade 10, and it does obviously spill over to our current grade, grade 11, and further continues in grade 12. Now, previously we learned acid and base reactions. Now, in acid-base reactions, we know that protons are transferred from one substance to another. Alright, we've seen that, okay? And especially from the acid, just a bit of revision here, the acid transfers a proton to the base. Okay, now reactions involving the transfer of electrons, alright, specifically the transfer of electrons from one substance to another. They are called oxidation reduction reactions, or in short, redox reactions. So, the ox part, we're going to start here. Okay? Ox part basically stands for oxidation. Okay? So, let's unpack what oxidation is first. Okay. Now, oxidation. Quite a long definition here. The substance which donates electrons is oxidized. And we form an acronym called OIL. Oxidation is loss of electrons. Okay, some other textbooks will describe it as LEO. Loss of electrons is oxidation. Doesn't matter. Okay, the original definition of oxidation was the gaining of oxygen. All right, for example, a type of oxidation reaction, okay, would be like iron rusting. All right, becomes oxidized. Right, if you leave an iron substance or iron pipe or iron whatever out in the open too much, for a long period of time, it will start to rust. In other words, the iron will get weaker. All right, it'll start turning a brownish color, and then leave it there long enough, and it will become extremely weak. So a lot of its contents has begun to, or not has begun, but is lost. And then let's have a look at the, let's pick another color for this, the red part, okay, which is reduction. All right, now, in short, well, not in short, let's maybe write it similar to how we wrote the top, okay? Now, reduction is the substance, okay, which accepts the electrons. Okay, that is called reduction, or the substance that accepts the electrons, that is the substance that is reduced. All right, in other words, it's the, like oxidation is the original definition is the gaining of oxygen. Reduction would be the loss of oxygen. So we form another acronym called RIG, R-I-G, okay, which basically, to help us remember this, is reduction. Let me write this a little bit clearer. All right, reduction is, I'll use a small g, gain of electrons. Okay, so those are the definitions. Okay, so the substance that loses electrons, oxidation. The substance that accepts or gains electrons is called reduction. Okay, now the oxidation reduction process can be represented by half reactions. Okay, so what we'll do is we'll leave this up for a little bit for the students to take down, and then we will move over to the next slide. I will do a bit of half reactions for some substances, okay, and then we'll tend to explain it with a bit of a drawing. What we must understand and remember is that with acids and bases, we looked at the transfer or the movement of protons, particularly hydrogen protons. All right, we looked at that. Now in redox reactions, we are looking at the transfer of electrons. Okay, protons are positive whilst electrons are negative, so they are two oppositely charged particles. Okay, two oppositely charged particles. So with redox, oxidation or reduction, we are monitoring the transfer rather, which substance is losing electrons and which substance is gaining the electrons. So we're watching two things here. Same like with acids and bases, we were watching which substance lost the proton, which was the acid, and the substance that gained the proton was the base. Okay, with redox, we are watching a transfer, which is losing, which is gaining, but we are watching the electrons now specifically. Okay, let's go demonstrate that on the other slide. So let's have a look at what is known as half reactions. Now, half reactions means we've got two reactions taking place. We've got a reduction half reaction, of course, and then we've got a oxidation half reaction. So if we start with the oxidation, which I'll keep in red, and let's pick a substance such as magnesium, which is Mg. Now, magnesium is a substance that gets oxidized. All right, in other words, it loses electrons. It becomes Mg2 plus 2e. All right, 2e with the negative on top, which is basically the symbol for an electron. Okay, so if this is now technically 0. Okay, this is stable. All right, now you lose 2 electrons. Basically, you are now twice as positive because you lost twice as much negativity. Does that make sense? Okay, let's kind of say that again. I use positive and negativity in terms of attitude because it the best helps students to understand. It's been working for about 5 years now, so I'm just going to keep it going. Also, it helped me. Okay, is that if I'm now 0, in other words, I'm a whole substance, okay, and now I lose 2 electrons, I'm now twice as positive because I lost twice as much as negativity. So now I'm 2 times positive because I'm basically less 2 times negative. Okay, let me take away these little white little rings here. In other words, in this reaction, I am showing that I lost 2 electrons because those are negative. Okay, I lost 2 electrons. They are gone. I've gotten rid of them. Okay, so I'm obviously twice as positive. They are gone. Remember, the definition for oxidation is loss of electrons. So this reaction shows that this substance has now lost 2 electrons. When it comes to reduction, I think I use this color, yes. Reduction will show which substance gained the electrons. Okay, so let's take, for example, sulfur. Sulfur plus 2 electrons, which is negative, of course, now becomes S, which is sulfur 2 minus. Okay, because remember, also had a 0 there. It accepted 2 electrons. Electrons are negative, hence 2 minus, showing that I accepted the electrons, and this is what I have left with. This is my new product after I've accepted the electrons. This over here is the product after I lost the electrons, especially. Okay, so notice they are written differently. Oxidation reaction is written in the same format as 2 is equal to 1 plus 1. Right? But reduction is written in the format of 1 plus 1 equals 2. Okay? So they're written differently, but as you can see from just using a mathematical sum, this either might confuse you or it might make you understand, but this is what helped me understand the difference between oxidation and reduction. This is my own method, my own tips, my own tactics. It might not work for you, but if you can understand mine, it might just. Obviously here, this Mg will represent this 2, saying that 2 is equal to 1 plus 1. Alright, so I'm actually writing this sum here, 1 plus 1 equals 2, like I know it, the other way around. Okay, for oxidation. But for reduction, it's a simple, straightforward 1 plus 1 equals 2. Boom. Two things coming together to get something new. Oxidation, something was breaking it apart. Okay, 2 is equal to 1 plus 1. 1 plus 1 equal to 2. This is just a tip. You can use it, or you don't have to. Okay. Now, in oxidation, we also get what is known as a net reaction, because remember, these are half reaction. So a net reaction is one reaction. Okay, net reaction. The net reaction is basically just the product of both. Okay, so I've got 2 electrons and 2 electrons, which are both negative, so they cancel each other out. And I'm left with everything on the left of the arrows, and I'm left with everything on the right of the arrows. So this will be the top one first, Mg on top, plus sulfur at the bottom. Obviously the arrow goes next, then Mg2 plus on top, plus S2 minus. This is now my net reaction as a result of one reaction being oxidized and another reaction that is being reduced. All right. So notice that in an oxidation half reaction, electrons are on the right hand side. Okay, they're here. So this is the electrons on the right hand side as they are produced. In other words, because they are, remember, the substance lost the electrons. So they are produced to go, whilst the reduction half reaction is on the left, because the electrons are on the left of the reduction half reaction, because they are used to form a new product. Okay. So what we have here is a little graphical example of an actual redox reaction. Okay. So what I have there is, judging by Fe here, you'll know that it's iron. So this is an iron rod. Okay. And it's placed in a copper sulfate solution. So CuSO4. Okay. And I've just drawn the ions in it. Now, when a piece of iron is placed in a copper sulfate solution, a reddish brown layer, which is this little reddish, I don't have brown, so I just drew red, is formed on the iron. Now, what this is if the iron is left in the solution for a number of hours, so this takes some time, okay? It doesn't happen in minutes. But if it's left there for a number of hours, a blue, or the blue color of the copper sulfate solution becomes noticeably lighter. In other words, it begins to clear up a little bit. Okay, it becomes lighter and the piece of iron becomes thinner. Okay, why is this the case? When a piece of copper metal, all right, is placed in an iron sulfate solution, no change will be observed. Okay, but if we have a look basically at, that was just a note, I just had to add that in there. But if we have a look at back to our actual reaction, why does the piece of iron rod become thinner after some hours and the copper sulfate solution begin to get lighter? The iron in the copper sulfate is oxidized. Okay, so iron is oxidized, okay, to form Fe2 plus ions, which is an oxidation reaction right here. Okay, and they go into the solution. Okay, whilst the copper 2 plus ions, Cu2 plus 2 electrons, as you can see, that gets reduced to solid copper, which is the collection of the reddish brown layer on the iron rod. Okay, they reduce to the copper solid or copper metal. Okay, now the decrease in the concentration of the copper 2 plus ions that's in the copper sulfate solution, which by the way is written as CuSO4. Okay, if you split them up, they are ionized like that. Now the copper 2 plus ions, okay, there's a decrease in concentration because all of these beauties are going over here, so there's a decrease in the concentration of the solution. Okay, and when there is a decrease in the concentration of the solution, okay, the solution starts to get lighter, clearer, okay, as a result of copper leaving the solution and collecting around the iron rod. Okay, So it's represented by these two equations, okay? And if we must form a quick net reaction here quickly, of course, they will cancel out. We will have Fe, which will be in brackets solid, okay, plus Cu 2 plus, which will be an aqueous solution, okay, it's going to give us Fe2 plus in aqueous solution plus solid copper. Okay, that's the reaction that is represented there. Okay, this is what takes place in this little jar, or is taking place in this little jar that is depicted on your screen right now. Okay, the disjoining. Okay, now what happens to sulfate? I don't know if that was a question in anybody's minds. What happened to sulfate, the SO4 2 minus? What was happening there? How come we don't see that included here? Okay, that in grade 12, there's a term for it, but I'll share it now since that some basically are grade 12s, as your current grade 12s have left school. They're basically not a part of the school anymore. Your matric here actually starts right now. It's called a spectator ion. Okay, I won't tell you why it's called a spectator ion. We'll save that for electrochemistry in grade 12, where we do redox reactions under electrochemistry. We'll explain why it's called a spectator ion, but that's the term for it. In other words, in layman's terms, it's not a part of the reaction. Redox it doesn't take part, it just stays there. Nothing happens to it. Now, oxidation numbers, or oxidation state of an atom or molecule. This will be the charge it would have if the electrons in each of its bonds belong to more, or belong to the more electronegative element. The best way to explain that definition, because I don't think that it is a question asked in the exam, we just rather need to understand how it works. If we have HCl, which is hydrochloric acid, the shared electron pair would be considered to belong, in inverted commas, to the more electronegative chlorine. Okay, now chlorine has got a larger or stronger electronegativity than hydrogen. However, we know according to the periodic table that hydrogen is in group 1 and has a charge of +1, whilst chlorine we know is in group, I don't want to misquote myself here, where's the periodic table? Don't want to say it's in the wrong group, so that's not a good look on me, so I'd rather just make sure. Get a periodic table out here. Chlorine, yeah, that's in group 7. Yes. So, of course, we know the groups goes in terms of electrons bonding 1, 2, 3, 4 up until the group where carbon is, and then 3, 2, and 1. So chlorine obviously makes -1, right? And both of them together equals 0. Okay. Now oxidation numbers, okay, provide a convenient way, or let's say just one way. So it provides a convenient way of following the transfer of electrons during reactions by finding out what is their, basically not their charge, all right, but knowing how but knowing basically how many electrons that they carry when bonding in the molecule. All right. So hydrogen, according to the periodic table, makes +1, whilst chlorine is -1. All right. So it's the charge on each of the elements in the molecule or compound. Okay. Now, there are rules when it comes to oxidation numbers, and I'll do an example as well to basically, another example to further show this method. Okay. The first rule is that oxidation numbers, which I'm going to abbreviate to ON, okay, of any uncombined element is 0. Example, O2, right? 0. Okay. O2 is uncombined with any other element, it's combined with itself. Right? It's 0. Okay. Second one, okay, is that the oxidation number. Okay, there's about 7 of them, okay, just warning you. Oxidation number of an ion, all right, of an element. All right, it's equal to its charge. Okay, for example, Cu2 plus, it's plus 2. Okay, that is the charge on it. 3. Oh, sorry. The sum of all oxidation numbers in a molecule is equal to 0. I'm going to shorten up the words a little bit and kind of make it a little more easier to write down. Okay. Sum of all, which is basically the same as on top here. Oxidation numbers, ON, in a compound ion. In a compound ion, basically is equal to the charge on that ion. We'll look at an example, probably a little later. Number 5, oxidation number of halogens. Okay, all halogens is equal to -1. Okay, brackets, when the compound consists of 2 elements. Okay, you know group 7 is our halogens. Number 6, I think I can fit it in there. Oxidation number of oxygen in a compound. So when oxygen is bonded to anything else, okay, oxidation number in a compound, okay, is nearly always equal to -2. All right. And then the last rule, which I will put down, the oxidation number of hydrogen in a compound is nearly +1. Okay, which is, as we saw here, hydrogen there, +1. Okay. But I would say 6 and 7, they kind of go without saying, but of course, 1 to 5 are the most important ones. Okay, they are the most important ones. Okay, we will take a look at a little bit of an example. Okay, and we'll look at another example, because what they like to ask is not, for example, what is the oxidation number of so and so, whatever. That is a fair question, but they'll give you reactions and they'll say which of the following are, whether the following are redox reactions or acid-base reaction, or whether the following are redox or not redox, which ones are redox, which ones are not, or just ask you out of 3 which ones are, and you got to prove and test which ones are. Okay, so let's have a look at a little bit of an example quickly, and we'll come back to this. We'll first look at an example. So let's say they ask you an example. They want the oxidation number. Okay, this is the question. Find the oxidation number of nitrogen. All right, in NO3 minus. In other words, they want it in the nitrate ion. Okay. Find the oxidation number there. Okay, so basically, first things first, the rule, we can see that this is the oxidation number, all right, of an ion, or the sum of all oxidation numbers in a compound ion is equal to the charge on that ion. Rule number 4. Okay, we see we have a compound ion here, and that is a negative up top, which is the same as -1. So that means that the oxidation number of nitrogen plus the just bracket this up, plus the oxidation number of oxygen all right, must be equal to not 0, but minus 1, because that is the charge on this entire compound. Okay. So, we basically find what is the oxidation number of, we basically got to find what is the oxidation number of nitrogen. So we don't know what that is, so we'll just leave it like that. But we know that the oxidation number of oxygen is 2, or minus 2. But we have 3 of them. So we're going to have N plus 3 times minus 2 equals to negative 1. Okay. The oxidation number of nitrogen, we don't know yet, but we know that is minus 6 is equal to minus 1. The oxidation number of nitrogen is going to equal to minus 1 plus 6. Therefore, oxidation number of nitrogen is equal to positive 5. Let's see if that makes sense. Okay, because in nitrate, in the nitrate ion, let's bring it up again, NO3 minus, we've got positive 5, 3 times minus 2, that's obviously minus 6, 5 minus 6 is equal to minus 1. These numbers match up, therefore we know that positive 5 is indeed correct. And that's how finding the oxidation numbers obviously work out. Alright, sorry, I moved my mouse there. That's how they work. Okay. Now, it's not always easy to see whether a reaction is redox or not. Okay. In a redox reaction, electrons are lost from one reactant and is gained by another. So there must be a change in the charge somewhere on the left, and from the left-hand side to the right-hand side. There must be a change. Okay, oxidation numbers are obviously useful to help us analyze whether there has been a change in the charge. If there's no change in the charge from left to right, from reactants to the product side of the reaction, we know that the reaction is not redox. If there has been a change, right, then we know that there is a redox reaction. In an oxidation number, all right, or in a, sorry, not an oxidation number, in a redox reaction, the oxidation number of one substance will increase while the oxidation number of another will decrease. So we're going to have to obviously watch out for that. Let's take an example quickly. I'll do one and then I'll give you one to maybe try on your own. Okay, let's just have a look and see what I mean by what I just mentioned. If we have an example here, let's take the reaction. Let's take a reaction. We've got HCl, the example, plus sodium hydroxide, a reaction we know very well, of course. And then we get table salts, NaCl plus water. Salt plus water, basically. Now we know this is an acid. Well, I wouldn't say it's an acid-base reaction, but I mean, you know, of course, what happened here, Na went to Cl, and of course, the hydrogen went over and formed water. Okay, now we need to check. So let me use another color. So we know the oxidation number of hydrogen is positive 1 and negative 1 for chlorine. Okay. We also know the oxidation number in any compound of oxygen is minus 2, whilst hydrogen is also positive 1. Let's just write down what we know. Chlorine is minus 1. Hydrogen, all right, is also positive 1. Notice that we do not write down positive 2. You can do this if you wish. Okay, because we've got 2 hydrogen. We are concerned with the oxidation number of hydrogen, not how many hydrogens there are. And that's minus 2 there. Basically, though, this helps us get to 0. So that's just what we know. So let's see if there's a change in the charge of sodium. All right, now sodium is in the same group as hydrogen. All right, so that's also positive 1. And on the right hand side, it's also positive 1, because here this equals 0. Oxidation number in any compound is equal to 0. That equals 0. Let me see, 1 plus 1 is 2, minus 2, that equals 0. and here this also equals 0. So can we see here that in this reaction, none of the elements have changed oxidation state? Okay, therefore this reaction is not redox. There is no change in the oxidation numbers from the left hand side of any of the elements to the right hand side. No difference. They have all the same. Sodium is 1 here and 1 there. Chlorine is -1 and it's -1 there. Left and right. Okay. Let's give another example. Okay. Let's write another reaction here. SO2 plus H2O gives us product H2SO3. Okay, let's see you all try this one on your own. Alright, let's unpack this one. So let's write down what we know. So we know the oxidation number of oxygen is -2. We just happen to have 2 of them. Okay, so I'll put a, usually won't have space for this, but I'll put a 2 times over here because I've got 2 of them. So I'll go to 2 times there. And this one I've got obviously 2 times +1, but the oxidation number is +1. I keep getting this wrong because there we go. And that's -2 for oxygen. And here we've got also 2 times +1. And here we got 3 times -2. Okay, so now obviously we define the oxidation number of the sulfur. Okay, so sulfur here, or for the oxygen, I'm going to have 2 times -2, so that's going to give me a total of -4. So in order for this to equal 0, sulfur is going to have to be +4. And over here, I've got -6. 3 times -2 is -6, and here I've got H2, which is 2 times 1, and that's +2, and this must equal 0. So if I solve that, equals to 0, that goes over, becomes +6, that goes over 6 minus 2. So sulfur here is also +4. So we can see in this reaction there is no change, so therefore it's not redox, and our reason is that there's no change in the oxidation numbers or the oxidation states of the elements in the reaction. We'll do one more example reaction. Let's take iron chloride. I will balance this reaction afterwards. Plus H2O plus SO2. That's going to give us H2SO4 plus 2H, no, sorry, let me balance that later, plus HCl plus FeCl2. Sorry, this must be a 3. Mustn't be a 2. This must be a 3 here. Okay, let me balance this quickly. This is 2 over here. There's a 2 over here. That's empty. There's a 2 over here, as well as a 2 over there. Okay, so let's try and find the oxidation numbers of these ones. Obviously, I will start you off. Okay, now the balancing numbers, we're not worried about that. That's got nothing to do with oxidation. Okay, so let's start off with what I know. Let me make my pen a bit smaller so I can fit maybe this stuff in. Okay, now chlorine we know is already -1. Okay, so I've got -1 there, multiplied by 3. So I'll put the 3 on the outside rather. This one we know is 2 times +1, that's -2. Oxygen here, 2 times -2. Hydrogen we know is 2 times +1, but its +1 is the oxidation number. Oxygen here, 4 times -2. HCl, we know that's +1 and -1 of HCl, and chlorine, you know, it's 2 times -1. Okay, so we're basically trying to find out the oxidation numbers of the sulfurs and the irons. Okay, 3 minutes. All right, let's do the solution quickly. So let's see, can someone else talk me through what is the oxidation number of iron in FeCl3? Alex, you already answered. No offense, but I want someone else to answer for this one because you answered on the second example there. So, anyone else? A Connor, a Kelly, or a Nadima who's in the class right now, maybe just pop me a oxidation number for iron in FeCl3. Okay, we know it's going to be a positive number. Okay, we know it's going to be a positive number. So I just need, which number in it, is it?
So for the iron, it's 2 plus 3.
Okay.
2 times positive 3.
2 times positive 3. Okay, so oxidation number will be positive 3 there. Lovely stuff. Okay. Anything else, Connor? Go for it.
And then for the other iron, it's also 2 plus positive 3. And then...
Sorry, Connor, did you say it is for this iron in FeCl2 that it's also positive 3?
2 times positive 3.
Okay, remember this balancing number has nothing to do with it, eh? It's just, that's just a balancing number. So there's no 2 there in this one.
Also, it's just positive 3.
Okay, cool. So, okay, it is a positive number, but just have a look at this one again for me. If chlorine here is -1, and I've got 2 of it, so 2 times -1, and that's -2, and they must equal 0, then iron should be not positive 3, but
positive 2.
Positive 2. Excellent. Because positive 2, obviously plus the -2 there, it's going to give us 0. Great. Shot for the irons, Connor. Okay, I'll hold you off there. All right. Okay, yeah, sure.
I'm not going to answer.
No, it's fine.
I'm not going to answer, but I just want to know what happened with the 2 in front. How come you're not adding that on to make -4?
I'll put it on as a thing. I'll put it on as a note here. Okay. Balancing numbers, which is the 2 here, this one, this one, this one, and this one. Okay. Balancing numbers are not a part of redox. Alright, or should I say more specifically, oxidation numbers. They are not a part of oxidation numbers. Okay, they have nothing to do with oxidation numbers. Balancing numbers are there to balance the equation. Alright, and for the mole ratio. They've got nothing to do with oxidation numbers.
But then how come you put the 2 in front of the positive 3? Because if you say 3
Which
plus, there, that one.
Oh, that's my mistake. That must come out. That's my mistake. Thanks for pointing that out. That should just be positive 3. I ignored my own rule there, or the actual rule, so apologize for that. That's just positive 3. It's not 2 times positive 3. Shut up. Okay. So oxidation number of iron in the first one is just positive 3, and the oxidation number of the second one is just positive 2. Positive 3 plus minus 3 gives us 0. Positive 2 plus -2 gives us 0. Okay, thanks for that. Okay, cool. So that's done. That's done. Now I just need someone to help me on the sulfurs, please. Okay. Guess that just leaves you, Kelly. Okay. Kelly, can you mind giving this one a shot quickly? What would sulfur be in this one? SO2. Let's just start with 1 quickly then. What would sulfur be in SO2? Plus 4 is correct. Positive 4. Okay? 2 times -2 is -4, so they balance it out. They give us 0. If that's the case over here, then Kelly, you are right that it's also positive 4 here, because here I've got positive 2 times. Wait, actually, let me make sure of that. No, it's not positive 4 there at all. Of course, I'm talking absolute bully. It would have been so if if we had like maybe an extra hydrogen or 1 less oxygen. But what would the oxidation number of sulfur be in H2SO4, please, Kelly? So this is 2 times positive 1, that's positive 2, and here I've got -8. So what would sulfur be in the middle here? What would that oxidation number be, please, Kelly? Positive 6, correct. Okay, because positive 2 plus 6 is positive 8, minus 8 gives us 0. Okay, now this is different from our other previous two equations, because in the previous two equations we saw that there was no change. But what did we notice? We notice a few things. The first change we notice is that iron went from positive 3 to positive 2. The second thing we should notice is that sulfur went from positive 4 to positive 6. One substance decreased in oxidation numbers, and in their oxidation number, whilst the other increased. So therefore, what can we conclude about this equation? First, iron, we have to mention it like this. Iron changed from positive 3 to positive 2, and sulfur changed from positive 4 to positive 6. Okay? There is a change of charge. Okay? There's a change of charge. All right? Therefore, redox. Or therefore, this is a redox reaction. All right? That's how we do it. Okay? Checking if the oxidation numbers of all has changed. And it's very simple once you know what the oxidation numbers of some of these are. So example, this one was easy, this one was easy. Even in H2SO4 plus 1 minus 2, 4 of them, etc., all equating to 0. Boom, boom, bada ba. Okay. Thank you so much for joining me tonight, grade 11s, in our tutorial video on redox reactions. And please don't forget to like and comment on this video, as well as subscribe to our channel, Good, Better, Best online videos. And we'll catch you in the next one.